Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, number of flowers in full bloom. We're given a 2D array basically of ranges. Like these are flowers, but each flower represents a start time and an end time, and it's zero index, but that's kind of meaningless because the ranges actually can start at 1. Like that's the smallest that a range is going to start at. Not that that really matters that much, but we're also given an integer array of people where each value of the person, like the ith person, represents the time that they arrive to see the flowers. And even that is a bit misleading because if they say arrive, that kind of implies that you could see all the flowers that come after that, but that's not really true. It's really more of a snapshot. At this time, the person at time 2 only gets to see this flower. And I kind of blew it up a little bit, but let's just understand conceptually what's going on here. So here we have a flower that starts at time 1 and ends at time 6. So that flower is kind of in bloom for that period. And we have another flower here that's in bloom for this period. And remember, a person can only see the flowers at the snapshot time that they are at. And for every single person, we want to map that person to the number of flowers that they're going to be able to see. So the first person here, we can see only sees one flower. The second person sees 2 flowers because the first one is still in bloom and the second one here just kind of came into bloom, so they can see 2 flowers. The third person here can only see 1 flower because the first flower is no longer in bloom after day 6, and this person arrives at day 7. And also they can see this other flower because it came into bloom on day 4 and it doesn't go out of bloom until day 13. And of course, this person is within that range. So really for a person, we want to make sure that the day that they arrive is greater than or equal to a flower and less than or equal to another, well, when I say flower, I meant like the starting range of that flower and the ending range of that flower. It's in that range. Now, for the last person here, this flower here went out of bloom, but this one came into bloom, so now they have 2 flowers to look at. So the result here is going to be 1 for this person, 2 for this person, 2 and 2. And that's what we get down here. Now, there's a couple gotchas for this problem. The main one is that the people in this case is sorted. The array of people is sorted based on the time that they arrive. And pretty much with every type of like interval problem like this, we always want to use sorting to our advantage if it's relevant. And in this case, it's definitely relevant. So one thing for sure is that we probably want to sort the array of people. And we probably also want to do some kind of sorting on the flowers as well. And remembering how we kind of just solved the problem just by drawing and like looking at it, what do you think we could do to solve this problem? One way is to use counting. What do I mean by counting? Well, for any particular person, we want to map them to how many flowers they're going to be able to see. So in other words, we want to count for any given timestamp, any given time position, basically. We want to know how many flowers can we count that are in bloom at that time. So we can keep a running count. How do we do that? Well, we probably want to, for like this person, this is the one we're starting at time 2. We want to know how many flowers come into bloom at a time that is less than or equal to 2, because what, like this person sees a flower just came into bloom. So if it's equal, that also works. But if it's less, that also works as well. So you tell me how many of these flowers, or even looking at the array down here, which I also am going to go ahead and like blow up, like looking at this array, how would we count the number of flowers that come into bloom before time 2? Well, we would just count the ones that have a starting time that's less than or equal to 2 in this case. And how many of these satisfy that? Well, just a single one. This one comes into bloom at that time. So we know 1 flower is going to be in bloom at this time. Now, for the second person, so far we have a count of 1. 1 flower is in bloom. Now, for this person, how many additional flowers are at a time starting at less than or equal to 3? Well, we already kind of started at this one, and among these 3, not this one, 4 comes after 3, and 9 also comes after 3, but this one here just bloomed at time 3. So now we can take our count and set it to 2. We're iterating over the people in sorted order, and we're just counting the number of flowers that started blooming. So this person would get a value assigned to 2. Now there's one part of the solution that we are missing, and that becomes very, very clear when we get to the third person over here at position 7, because now we already know that this one started blooming, this one started blooming, and this person is at position 7, so 9 is not less than or equal to 7, but 4 is less than or equal to 7, so this one also starts blooming. But that doesn't necessarily mean our count is 3, right? We don't assign this person a value of 3, and that's because we know that sometimes flowers are going to go out of bloom as well. So not only should we count the number of flowers that come into bloom, which we check like this. We check that the people at position I is less than or equal to the start of the blooming flower. So this is how we count that a flower started blooming. How do we know that a flower finished blooming relative to a person? Like, how do we know for this person that a flower is done blooming? Well, we check that the end is actually less than people of I, not less than or equal, less than. That's very important, because if it were equal, that would mean we're kind of at the cusp, like at the edge of it. And this definitely is valid, but this one is definitely not valid. So that's why we have equal, not less than or equal. So what I'm getting at is, not only do we have to look at the starting positions, but we also look at the ending positions, and we see this time that 6 has a ending position less than or equal, or just less than 7. So this time, this is no longer part of the current position. So our count is actually going to be decremented down to 2 now, and that's the value that this person is going to be assigned. And just to finish the example, when we get to the fourth person here, we get another flower that is done blooming because it's this interval, right? This one ends at 7, but we know this person is at time 11, so this one is done blooming, but we also get one that started blooming at 9, which is less than 11. So we know one just started. So this one is also part of our range. So basically our count stays as 2. We removed one, but we also added one. So that's the value that this person gets assigned. And now the only question we kind of have is, well, how do we accomplish what I just talked about? Like, how are we going to know when a flower started blooming and it stopped blooming, and how can we do it efficiently? Well, we are kind of using sorting. At least we're using heaps. That's the easiest way to solve this problem, because heaps will, of course, add a sorted property to the flowers. And what I'm actually going to initially do is have 2 heaps, one heap for the starting times and another heap for the ending times. And both of them are going to be min heaps because, of course, we're going from left to right. We want to go through them in sorted order. And every time we pop from the start heap, like both of these heaps are going to be initialized with all, well, the start heap is going to be initialized with all of the starting times, and the ending heap is going to be initialized with all of the ending times. And we're basically going to do what I showed in the drawing explanation. We're going to pop from the starting heap, and that tells us that a flower just came into bloom. And in that case, we would take our count and increment it. But every time we get a flower that goes out of bloom, we're going to take our count and decrement it. And that will always tell us for any given person what our current count happens to be. Now, knowing that, I'm going to go ahead and code the solution up, but I'm also going to show that we can solve this with one heap. That's a simplification we can make. And I'm also going to talk about the time complexity a little later on, because I kind of disagree with Leetcode's editorial, at least how they analyze the time complexity for this solution. But let's get into it. Okay, so we know we're trying to build a result which is going to be the same length as the array of people, because of course we want a value for every single person. So that's what I'm going to initialize here, just an empty array of all zeros. That is the same size as the length of people. And we're doing this because we're not necessarily filling in these people like this from left to right, because we want to go through the people in sorted order, and it might not necessarily be sorted. So what we're going to do here is get people and actually convert it into a array of pairs. So the person and the index of that person. And we can do that in Python pretty easily like this. So for I, P in enumerate people. And then when we actually iterate over people, we're going to do so in sorted order like this. We're going to sort it and then iterate over a people. We're doing that because we're also going to be maintaining a count, which I'm going to initialize to 0. And we know on every iteration of the loop, we're going to calculate what is the count for this particular person, which we know their original index was index I. That's why we're kind of adding this index here. We want to know the original index for every single person, because once we calculate the count, we're going to fill it in like this. We're going to say result at index I is going to be equal to whatever the count we computed for that person. So this is what I mean by we're not necessarily filling this in from left to right. If we were, we would just be able to do something like this. We'd be able to say result.append whatever count we computed, and we wouldn't have had to initialize this array like this. But now the only thing left for us to do is initialize those two heaps that I talked about. So I'll do that, and it's pretty easy in Python. So the first thing we know, we're going to need a start heap for all the start times. And in Python, we're going to initialize that first like an array. And we can do that again with list comprehension, just like we did up here. So here we're going to say for the f in flowers, and we want the start time. So here we're going to put f of 0. And we're also going to do the same thing for the end times. I'm going to copy and paste this here, and this is going to be called end, and this is going to be index 1 because we want the end time for that flower. Now, to actually convert these into heaps, we're going to run heapify just like this, heapq.heapify on start, and do the same thing for the end. And this is an O of n operation where let's say n is the number of flowers. And of course, we are doing sorting on people. Let's say we have m people. That's going to be m log n. And I guess I might as well add now that we're going to be returning the result because we already know that. But now, what are we going to do inside the loop? You can see we had to do quite a lot of pre-work here, a lot of pre-processing, but the rest of the code is going to be pretty straightforward. For this person, we want to know how many additional flowers came into bloom before or at the same time as this person. How can we do that? Well, we're going to say while the start time at the minimum start time in the heap right now is less than or equal to P, which is the time of the current person. While that's true, a flower came into bloom. So we're going to pop that flower now from the heap. So heapq.heap pop from start, and we're going to increment the count because a flower came into bloom. Now, one more thing here. What if the heap was empty? We can't access index 0 if it's empty. So before we do that, let's make sure to add start and then only check this condition. So we know flowers can come into bloom, but they can also go out of bloom. So for that, we're going to have while end, and what the other one was, the ending time of the minimum ending time of all the flowers is before the current person. It's before, that means the flower went out of bloom. We can't check if it's equal because it's technically still in bloom for this person. So that's why we have less than here. And if that was the case, we know once again, we're going to pop from the heap, the ending heap, and we're going to decrement the count like this. So minusing the count. We know for sure the count will never become negative because that's kind of assumed of the flowers. There's no way a flower is going to go out of bloom before it comes into bloom. And that's why this solution is going to work. So I'm going to go ahead and quickly run it to make sure that it works. And as you can see on the left, yes, it does, and it's pretty efficient. Now, I want to talk about the overall time complexity of this solution. And I'm going to kind of gloss over the fact that we're running heapify because this is not going to affect like the overall time complexity. The main things affecting the time complexity, one is sorting here. And let's say we have m people, that sorting is going to take m log m. And we have two heaps here. Assume heapify is O of n, where n is the number in the flowers. So that's not going to affect the time complexity, but in the worst case, we might have to pop every single value from one of the heaps. Again, let's say there's n flowers. That's going to be log n for every single pop. And if we do that for every single flower, it's going to be n log n. Technically, we're doing it for 2 heaps, so it could be 2 times n log n, but that doesn't affect the overall time complexity. Now, if you look at the Leetcode editorial, they actually argue that the time complexity is different. They actually argue that we should add another term here for m log n. And the reason, so I'm just showing this here, that this is just another way of writing what I'm writing right here. But the reason they are saying that is because they argue that if there's m people and we're iterating m times and possibly popping every single time, that we should add a term for m log n. But I, first of all, completely disagree with that, because there's no way we can pop more than n log n times. Like I kind of just talked about why that is. We can't pop more than we added to the heap in the first place. And not only that, but we know that n is going to be much smaller than m in the worst case, because if you read the problem description at the bottom here, they say that the length of flowers is going to be 5 times 10 to the power of 4, but the length of people could be up to 10 to the power of 9. So in the worst case, maybe you could argue that we should add another term here for m, but there's no way we should add m log n, because there's no way we're going to execute that many log n operations. I mean, we don't have that many flowers to pop in the first place. So I disagree with Leetcode's time complexity for this. Let me know if you think I'm completely wrong, though. Now, for the slight optimization that we can make, we actually don't need 2 heaps. We don't need the starting heap in particular. So what I'm going to do is get rid of the lines pertaining to the starting heap here. The reason we don't need that is because we can just sort the array of flowers based on the starting interval. And if we do a flowers.sort, that will kind of do that by default. It'll sort these based on the first, like the starting time of every single flower. And the reason we don't need to do that is because why not just iterate over the sorted array of flowers? And I'm going to have another pointer for that. I'm going to call it j. I'm going to have j equals 0, and that's going to tell us which flower we are currently at. So instead, alternatively here, what we can actually do is iterate while flowers at index I and the starting time of each flower is less than or equal to the current person that we're at. We don't need to push all the starting times into a heap because we can just iterate over them in sorted order. Now, every time a flower is in bloom, we actually are going to add it to a heap. We're going to add it to the end heap, but that tells us we probably didn't need to initialize the heap in this way. So I'm going to clean up these lines as well. And here I'm going to say heap q dot heap push to the end heap, the end time of the current flower at index I, and we know that the end time is at index 1. So that's what we're doing here, and then we're going to take I and increment it by 1. Now you might be thinking, don't we also need to increment the count? No, we're actually going to get rid of the count now, and the reason we're doing that is because the length of the heap is going to tell us how many flowers are currently in bloom. So we're going to change here to length of heap. But we also need to remember that flowers do go out of bloom. And for that, we're going to say while the end time of the heap, or like the shortest end time, is less than the person. So similar logic that we had before, just using one heap this time. And while that's the case, we're going to pop from the heap q.heap pop from the end heap. Again, we don't need to update like the count here because the length of the heap is going to tell us that. Now, there's a couple things we kind of missed. What if we go index out of bounds here, like I goes out of bounds? So before we do that, let's check I is less than length of flowers, and this is the case. And here, let's check that the heap is non-empty before we get an index out of bounds error here. Oh, and I had a very dumb bug here. I don't know why I used I. We should be using J, so I apologize for that. So all of these actually should be J, anything pertaining to the flowers. The only time we want I is when we are assigning this person's result. So I apologize for that. And a couple more typos, unfortunately, here. Person should actually just be P because that's what we're using to reference the current person. And here, length of heap. I don't know why I said heap when the name of our heap is actually just end. Now let's go ahead and run this to make sure that it works. The main observation though here is that we just need one heap. It's pretty much the same solution, just a little bit less code. So let's run it. And you can see on the left that yes, it does work. Thanks for watching. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.